Let's go over the practice quiz on chemical reactions. In the first section on the practice quiz, you're going to need to be able to identify the 4 different reaction types we've been covering. Synthesis, when you're taking smaller pieces and building one larger one, so typically you'll see multiple reactants but just one product. Decomposition, which is the opposite, so you'll start with one reactant and end up with multiple products. Single replacement, when you have one element by itself and another compound, and on the product side you're going to have a different element by itself, and that single element from the reactant side will now be in the compound. And in double replacement, you're going to have 2 compounds and they're going to switch partners when they get to the product side. So let's look at our first example here. We have H2SO4, that's a compound, and NaOH, another compound. And on the opposite side, we have sodium with sulfate, a different compound, and hydrogen with hydroxide, which is really just water, but it's nice to look at it this way to see all its parts. So as you can see, the hydrogen that was with sulfate is now over here with hydroxide, and the sodium that was with hydroxide over here is now with sulfate. So they've switched partners, and that means that is double replacement. On to the next example. In the next example, we have KClO3, one compound, and on the product side, multiple products. So that's going to be decomposition. Next one, we have barium and nitrogen, which come together to form BAN. So we've started with multiple reactants and ended up with one product. So that's synthesis. We've built something. We've made something from smaller pieces. Next one, we have sodium with phosphate, zinc with sulfate, and on the other side now sodium is with the phosphate that used to be with zinc, and zinc is now with phosphate. So this would be an example again of double replacement. Next example, we have potassium by itself and then hydrogen with hydroxide. And on the product side, we have hydrogen by itself and potassium with hydroxide. So that is a single replacement reaction. On to the next one, where it started with one reactant and ended up with multiple products. So that decomposed, that's decomposition. And then our last one here, we have mercury with nitrate and sodium with iodine. And now mercury is with iodine and sodium is with nitrate. So they've actually switched partners from one side to the other. So that's another example of double replacement. All right, in the next section here, they're asking about energy and heat. So this is going to be our heats of reaction. So we're going to pull in our table I. So here's table I, and we're going to be looking for this reaction where we have hydrogen and iodine gas forming 2 molecules of HI. So I'm going to zoom in on this so we can see it. We're looking for hydrogen and iodine gas. Here it is right here. It looks just like it does here, so we're not going to have to worry about switching signs or anything. And you can see that the delta H given is positive 53. Whenever the delta H is positive, the heat is actually going to be a reactant. So I'm going to put my 53.0 kilojoules as one of my reactants. And put this away for a second. And that means that delta H, which we can kind of think is equivalent to potential energy, because whatever happens to delta H is going to happen to potential energy. Since delta H was positive, potential goes up. Positive, potential goes up. And that kinetic must go down because the overall energy in the system can't change. All right, next one we have 2C and H2. And there's a couple like that, so we have to be careful. It's not this one because there's a 3 on the H. It's not this one because there's a 2 on the H, but here's one, C2H2. All of the phases of matter are the same, and it's positive 227.4. So once again, That's going to be a reactant, 227.4. So we're going to put that on the reactant side. And then once again, whatever happens to delta H, that's what's happening to potential energy. So that went up. So kinetic must go down. Next one. I'll line that one right up. So this is this reaction right here. You can see that it's negative. So this one, delta H, is negative. That does not mean, however, that you're going to put it into the reaction as negative. That's only telling you which side of the reaction arrow to place it. So I'm going to put plus, because it's going to be a product, 3351 kilojoules. And then as we said before, whatever happens to delta H is pretty much what's happening to PE. Since delta H was negative, potential energy will decrease. And then because the total energy of the system needs to be the same, kinetic must be increasing. One more question in this section. N2 plus O2 yields 2NO, which this isn't expanding for me, but I can see it on here. Right here. Be careful. There's a couple that look similar, and this one is positive 182.6. So because it's positive, it's going to go on the reactant side, 182.6 kilojoules. And then because delta H was positive and the same thing happens to potential, that goes up, kinetic goes down. And that's the end of that section. Next section, we are going to complete these double replacement reactions. So we're going to link up lithium with hydrogen carbonate and aluminum with carbonate. One thing I think it would be a good suggestion for everybody is to actually put parentheses around the polyatomic ions if there isn't already. And then whatever is inside the parentheses is going to go to the other side. The subscripts that are not inside the parentheses, like this 2 and this 3 on the outside, those aren't going to the other side because those are based on the oxidation numbers of the other elements or polyatomic ions they're already associated with. So on the other side, I'm going to put my lithium with the hydrogen carbonate. And then we need to look up oxidation numbers. Lithium is a group 1, it's +1. Hydrogen carbonate, when you find it in table E, is -1. So in this case, if you didn't record those parentheses, you'd still be correct, but I always think it's a good idea to do it anyway. And then our other compound is going to be made from aluminum and carbonate. Aluminum has a +3 oxidation number. Carbonate, when you look in table E, is -2. Those two exponents, our oxidation numbers, don't cancel out. They do not have a common factor to pull out, so we just swap and drop. The 2 goes on the aluminum, and the 3 goes outside the carbonate. You may notice that these don't balance at this point, and that's okay. I'm not going to ask you to do that in addition to coming up with the products, but you do need to find any precipitates if there are. So we're going to need to look at table F. So now we're going to pull in table F. I tend to ignore the metal part of the compound and look it up based on the other half of the compound because most of the negatives are actually listed already in table F. So I'm looking for hydrogen carbonate, and I'm going to start in the first column here with things that are soluble. Oh, and here's hydrogen carbonate right here. So that means it will dissolve, and there's no exceptions to that, so that is not going to be our precipitate. The other compound we have here is a carbonate. Again, ignoring that metal to start with and looking at the carbonate. So here we go down our first column. Okay, don't see it there. This second column is just exceptions to the first. So, oh, here's carbonate right here. So carbonates are typically insoluble. We just need to check and make sure, because aluminum is combined with it, that there is no exception to that that includes aluminum. Aluminum is not a group 3. It's not ammonium. So it is just simply a carbonate that is insoluble in water. That is actually going to be our precipitate. So just like the instructions say, we are going to circle it. It's going to precipitate out. It's going to make our solution cloudy. Next example, once again, our outsides are going to come together and our insides are going to come together. And I suggest that you put your parentheses around your polyatomics so you don't bring over things you shouldn't and you don't leave out things that you should. All right, so we're going to put Mg with PO4. And magnesium is a group 2. It has a +2 oxidation number. Phosphate in table E is -3. Those oxidation numbers do not cancel out. They do not have a common factor, so we're just going to swap and drop. And then our other compound is going to have ammonium, one of our very few positive polyatomic ions, and sulfate put together. And looking in table E, ammonium is +1, sulfate is -2. They don't cancel out. They don't have any common factors to reduce them. So you swap and drop and you get a 2 on the ammonium. All right, now we need to see if we have a precipitate. So I'm going to start with the magnesium phosphate. So looking in table F, we'll look for phosphate. Nothing there. Oh, here it is. I see it. Phosphate. And we just want to make sure that since it's combined with magnesium that it's not an exception because it should be insoluble. And sure enough, it says it's an exception if it's a group 1. Well, magnesium's a group 2. So it is insoluble in water, and we're going to circle that. Then you should probably make sure, although like I've said, I've never seen a reaction with 2 precipitates, but I suppose anything's possible. Ammonium, I remember seeing that in the table, but we can go ahead and look it up based on sulfate like we normally do. And here is sulfate. Sulfates are usually soluble, and ammonium does not make it an exception. So that's going to go ahead and be soluble. All right, next one. Again, outsides are going together, insides are going together. And then I'm going to put my parentheses around my polyatomics to be sure that we bring over what we need to and don't bring over anything we shouldn't. So potassium is going to end up with acetate. Look up the oxidation numbers. They cancel out. So once again, if you didn't have the parentheses, you wouldn't be wrong. And then silver is going to be with chromate. Look up the oxidation numbers. They don't cancel out. They do not have a common factor. You swap and drop. And then one last time, looking in table F, look it up based on acetate. Oh, here's acetate right here. Always soluble, absolutely no exceptions. So let's go ahead and look up chromate. Here's chromate. It's typically insoluble. We want to make sure silver doesn't make it an exception. Silver is not a group 1, calcium, magnesium, or ammonium, so it is a simple chromate that is insoluble, meaning it would precipitate. By the way, if you ever forget what insoluble means, you'll notice the asterisk here next to insoluble compounds. If you look down here, it says they have very low solubility, which means that they will precipitate. And we're done with that page. On to the back. So these are single replacement reactions, and you're going to need to predict if they will happen spontaneously. We're not asking you to come up with the products, although you should be able to. So we're just going to need table J. So here's table J. And to know which column you actually need if you're comparing metals or nonmetals, you need to look back at your reaction. Find the thing that's alone. In this case, the thing that's alone, the thing that's not in a compound, is a metal. So we're going to compare it to the metal in the compound. So we're looking for nickel, which is Ni, and here it is, and silver is Ag. And the more reactive metal in this case is going to be nickel. So you need to ask yourself, would chlorine dump silver for nickel? And what always needs to happen is that the more reactive metal ends up in the compound. So if it's not already in the compound, a reaction is going to occur to put it in the compound. So in this case, yes, a reaction will occur. And your reasoning can just be nickel is more reactive. Next one, we have chromium by itself, which is a metal, so we're going to compare that to strontium in our table. Here's strontium up here, and then chromium's way down here. So our more reactive metal in this case is strontium. It's already in the compound, so we're going to say no, and the reason why is strontium is more reactive. We have chlorine alone, so that's a nonmetal. We're going to compare it to the nonmetal in the compound. So we're looking between chlorine and bromine. So chlorine is the more reactive nonmetal in this case. Since it's not already in the compound, then a reaction is going to occur. So we're going to say yes, and the reason why chlorine is more reactive. So we're done with Table J. Our last questions are going to be balancing questions. So like I showed you, I'm going to do that here. Of course, if you have another way that works, you can go ahead and do it your way, but you do need to show work. If there's no work, there's no credit. And that does say that right here. You must show work. So I like to list my elements underneath the reaction arrow, and then I start tallying. Iron, there's 1 on the reactant side, 1 on the product side. Chlorine, there's 2 on the reactant side, but 3 on the product side. Whenever you have an odd number, subscript versus an even number, there's no way you can ever make the even number one odd. So you want to get rid of the odd. And to do that, I'm just going to go ahead and I'm going to put a 2 out front here, because if I double it, I'm going to get rid of that odd number, and I'll have 6 chlorines. But in the process, I've now changed the number of irons as well, so now I have 2 of those. So I've messed up my irons, even though they had originally been fine on both sides. So now to fix chlorine, I can put a 3 out front here, and now I have 6 chlorines. And to fix iron, I just need to put a 2 out front there, and now everything is balanced. Next example, this one's pretty scary looking. Well, I want to show you something, though, that you can do. You'll see that this is a polyatomic ion, and it shows up on this side. And this is a polyatomic ion that shows up on this side. And nowhere have they been broken up. In fact, this is sort of a modified double replacement reaction. Some of the iron gets left behind here with the potassium, but the polyatomic ions are not broken up from one side to the other. So to make this one a little easier, you can actually list the polyatomic ions as if they're one thing. You could only do that if they haven't broken up from one side to the other. That's the only time this will work. I wanted to do an example to show you in case you get a harder one like this at some point. So now I'm just counting my atoms on either side. Now when I count my polyatomics, I'm actually looking at the subscript here. So I have 3 sulfates on this side, and on the other side, since there is no subscript, there's just 1. Subscript outside the parentheses on the sulfate. And then potassium, there's 1, but on the other side we've got potassium here and here for a total of 5, which is kind of obnoxious. So I'm going to avoid potassium if I can. And then SCN on the reactant side, there's just 1, but there's a subscript of 6 on the product side. So nothing's really working out very well, but you can start anywhere you like. I think I might start with iron this time, and I'll put a 2 out front here to fix my irons, but then that messes up some other things. So now my potassiums, I have 2 times 3, which is 6 potassiums there, and 2 more there, which is 8. And then my iron I fixed, it's now my SCN 2 times 6 is 12 SCNs. I'm going to try to avoid K and deal with SCN. So I'm going to put a 12 here to fix that. And then it messes up my K's even more. So now actually all that's off is our sulfates. So let me see, if I put a 3 out front here, I fix my sulfates. And then I have 3 times 2, which is 6 Ks there, and 2 times 3, which is another 6 Ks there, which means I have my 12, and everything is balanced. I suggest you do put a 1 here just in case they ask for the sum of the coefficients. You don't want to get that wrong, especially after all that work. All right, next one. We have 2 on the reactant side, 1 on the products, 6 and 2. And look at that, oxygen's going to be annoying and have multiple places on the product side. So you can see there's 2 here plus 1 there. So I'm going to avoid oxygen and hope it comes in line as I fix everything else. I'm going to start with carbon, but you could probably start with hydrogen if you want. And I'm going to put a 2 out front here to fix my carbons. But now I've messed up my oxygens. I have 2 times 3, or it's 2 times 2, which is 4, plus 1 more is 5. So now I have 5 oxygens on the product side. So now I think maybe I'll deal with the hydrogens, and I want 6, so I'm going to put a 3 out front, and I've got my 6, but now my oxygens are off again. So I have 2 times 2, which is 4, plus 3 times 1, which is 3. 3 and 4 is 7. That's not looking good. So that's 7, which is an odd number, which we can never make happen on the reactant side because the subscript is a 2. So maybe we should try doubling things to get rid of our odd number. So I'm going to make this a 6. And now I've messed up my hydrogens. I have 12. And then my oxygens, I have 2 times 3, or 2 times 2 here, which is 4, plus 6 more here, which is 10. And 10's maybe a little easier to deal with. Let's see what happens. To put a 5 here, I would get my 10, but I probably should have avoided oxygen because my hydrogens are still off. So if I put a 2 here, now I have my 2 times 6, which is 12, but now I have 4 carbons, so I need to change this to 4. So that's now 4. But I've messed up my oxygens again. So 2 times 4 is 8 plus 6. I have 14 oxygens, which actually if I just switch this to a 7, I'll get my 14. That was pretty tough, but I'm glad we stuck it out because we got the right answer. Before you really finish and decide you're good, you want to check and make sure that they don't have a common factor that can be pulled out, because if they do, you need to reduce them, because the answer always has to be in the lowest whole number coefficients possible. Now, these don't have a common factor because of that 7, but if they did, we would need to reduce it. I'm going to double check the other ones just to confirm. This has a 1, so definitely cannot pull out a common factor. And this one, the 3 kind of messes that up. So everything is done. It looks great, and good luck on the quiz.